Okay, good morning. Can you hear me?
可以，老师有声音。
Okay. So since last 2 week, we already give you some brief idea about the spins because this physical property is very important to the following class. So I just tell you that you need to understand this basic idea of spins. And now we are go ahead to the following chapter. Is about the first thing is I want to show you the practical application or practical uh, things that you may use the concept of spin in the application. The first one is magnetic field measurement. So I think it is a very important quiz that how to measure the magnetic field. Uh, in the reality, you may measure the magnetic field by using the Gauss meter, which is a device or instrument that can measure the stress and the direction of the magnetic field. But how does it work and where can we find it? That would be introduced in the following slides. Okay, so if you want to measure the magnetic field, you must know what is called the Hall effect. And the Hall effect is as shown here is a thin plate, and this plate may be made by a metal or semiconductors. Mostly they are semiconductor. And this device we will okay, for example, here is an coordinate, okay, x, y, and z. So if we inject the current from along the x-axis, so that would be from the left to right, and when we have a cross field, that is a magnetic field pass through this plane, so the magnetic field will be go through the y direction. Then we will find one thing, that is if we think there is a charge carrier is a path movement of the electron from the right side to left side, but it's virtually like there is a positive charge moving from the left side to right side. Okay, so when we have this situation that current inject from along these directions and the magnetic field pass through this plane, then the positive charge will feel a force. You may use the right hand rule, and you will find the force will be go upward. Of course, we know the charge will feel the Lorentz force with these equations. The F is equal QE plus V cross B. So there are many charge will accumulate at the top of the plate, and in contrast, if the positive charge go to the upside, and at the bottom they are all negative charges. So they will build an internal electric field here, and stop the positive charge continue go to the upside. So finally, they will become the balance because there's an internal electric field from top to bottom. So in this Hello?
老师目前这边没有听到你的声音，但老师你的麦克风开的。
Okay, can you hear me?
老师现在可以了。
Okay. I think I don't know why my screen freezed. Okay, wait a moment. I cannot control my PowerPoint slide. One more second. Okay, I just reconnect my USB. Okay, everything seems good. Okay, let me explain that again. So, when we apply a magnetic field, pass through this thin plate along the y-axis, and if there is a current that inject from the right side to left side, then the positive charge will feel a Lorentz force from the magnetic field. So you can apply the right hand rule and find the magnetic field will give you the force toward to the upside. So the charge will accumulate at the top of this thin plate, and in contrast, the negative charge will accumulate at the bottom of this thin plate. So they will build the internal electric field from the top to bottom. So this force comes from the internal electric field will balance with the force comes from the magnetic field. So finally, the positive charge will go straight from the right side to left side. Okay, at these situations, we can measure the voltage difference between the bottom to top. Then we will know the quantity of the applied, the magnitude of the applied magnetic field. So of course here is some detailed direction, but I just want to tell you that we can start from it very simply like this, okay? And the VH is the voltage difference of the whole voltage, okay? So VH means that the voltage difference from the top to bottom. So that would be correlated with the electric field and its width. So VH is equal to EW. And the EW is also associated with the electric field that we built. So this electric field is equal to the drift velocity. VD is drift velocity of the positive charge. Okay, so E is equal to VD times B. Okay, so we insert this equation here and substitute the E, so we got the VH is equal to VdBW. And the injected current is equal to the charge with its drift velocity, and the list N is the number of electron density. So here is a total charge move from left side to right side. And we also need to consider about, because this is the density, right? We need to count the actual number. So the density of the charge that pass through a certain area, which is here. Okay, there is a cross section here, so that would be T times W. So if we insert this equation, if we move this equation here and insert I to this equation, then we will get the Vd is equal to I by NQWT, and therefore we know the VH would be equal to IB by NQT. Okay, this is a very simple equations. So we know the thickness of this thin plate, and we also know the unit of a single electron, which is 1.6 times 10 to the minus 19 coulomb. And we can calculate the electron density or carrier density in here. Okay, or in contrast, maybe we already measure the VH. We know how the current that we inject. We also can control the magnetic field we applied, so we can get the density of the charge carrier. So if there is any field parameter you want to measure, that you can vary it here. There is 4 parameters, so you can get the parameter that you want. But here we want to measure the magnetic field, so we can choose one material that you already know the carrier concentrations, and you can inject the current that you can adjust a little bit, and you can measure the whole voltage cross button and the top. Then you will know the magnitude of the magnetic field. Okay, so this is the principle how to measure the magnetic field. Okay, so this is the actual device that is we call the Hall IC, and this Hall IC it look like this. So we can apply the current to this IC and measure the voltage difference here. But in the practically we will just control the voltage that we applied and measure the voltage difference between the voltage supply would be applied in the pin 1 and the pin 2, and then we will measure the voltage difference from the pin 2 and the pin 3. So there is a conversion table that will tell you the relation between the magnetic field that measured to the voltage difference between the pin 2 and pin 3. So this is the actual Gauss meter that would be look like this. So unfortunately we cannot show you in the classroom, but at least you may see this is the typical Gauss meter, and there is a prop here. We know we will see the Hall IC just located at the top of this rod. Okay, actually maybe you can make a try. If you have a cell phone, you can go to Google Play or Apple Store and looking for this app, which is called the Fifox. and this is devised by the Aachen University in Germany, and it can call out the function of the magnetometer in your cell phone. So you can measure many things, especially for the DC magnetic field. For example, I can show you here. Just wait a moment. Okay. Okay, just wait a moment. I will share my experiment. Okay, let me go to here, and we will. Okay, this is the actual screen that export from my cell phone. So I will start the experiment here. When I just press the play, then you will find we can measure the magnetic field from the Earth. So if I change the orientation of my cell phone, you will find there will also have some changes. And also, of course, I can measure the absolute value here. So you will find, wait a moment. So how can I change? Okay, I can just stop. Okay, remove the data. And okay, here, I just try again. Okay. Okay, so I just okay. Here we can see the absolute value of my cell phone. So the number here, okay, I'm sorry about there's some many Chinese character, but shown here is in the unit of a microtesla. Microtesla, which is one Tesla is 10 to the minus 4 Gauss, and the microtesla would be 0.01 Gauss. So shown here, it'll tell you the magnetic field of the Earth in my house is about 67 Gauss. Typically in the Zhongli area, the magnetic field from the Earth would be properly 38 Gauss. So you can download this app and measure that by your own, and you also you can measure the magnetic field inside your house, then and find out if there is something abnormal. Okay, so this is a typical application of the Hall IC and Hall material. Actually, that would be really important because you can imagine that nowadays all the cell phone would contain Hall IC because you want to navigate on the Google Map, right? When you drive, you need to know your orientation, especially where is the north. So I think most cell phone would embed it with the Hall IC, and you can use that not only to measure the magnetic field but also in the navigation. Okay, any questions? Oops. No. Okay, so I think you already know the Hall IC, and maybe if you are interested, you may try that in your cell phone. Okay, there is another very important devices that we can measure the magnetic field, which is a superconducting quantum interference device. In abbreviated, we call that the SQUID. Okay, the SQUID is using some material we call the superconductors, and there is a very special phenomenon that is if we make the this circuit with a superconductor, and when we put some insulator and in between these two superconductors and become a loop, then there would be a very special phenomenon that is if we change the magnetic flux inside this loop, then there would be a fluctuation in this when we measure this current. Okay, that would be something like this. Okay, the for the superconducting for the SQUID, they can measure the magnetic flux individually. What does that mean? Because the magnetic field would be quantized by the superconducting current. So you can for example, you can imagine that when I inject the current here, there's a 50% possibility go through this route, and then another 50% go through here. So they are equal possibility go to these two routes, right? But when I have magnetic flux pass through this center, then you can imagine that you can use the right hand rule, and for the length law, we would like to against the increase of the magnetic flux. So we will build an currents like this clockwise. So if we have a clockwise current, and for the IB, the total current here would be decreased, but for the IA, the total current would be increased because there is a loop here. A loop current here comes from the Lenz's law. But the most important problem is for the superconducting currents, there is a phenomenon we have a Cooper pair, which is combined by two electrons. And these two electrons, when we pass through this barrier that made by the insulate, then there's a quantum tunneling here. So we will find the voltage will be varied with the something like a sine wave. So if we can count this sine wave, or we can count the voltage difference between here and here, then we can know the the number of the magnetic flux. So this is the principle how the SQUID measure the magnetic field. Okay, the detail is a little bit complex, but I think that just tell you a very basic concept about a SQUID. Okay, this is a typical sketch of here. Here is this insulator in between these two superconductors we call the Josephson junction, and the magnetic flux here will be changed the number of current pass through this side and this side, and this difference will create a voltage difference here, and that would be oscillating voltage. And this is another picture that is SQUID, and we can measure or eject the current from the gold electride. And this is a practical. This is a real machine that made by SQUID, and it is the most accurate instrument that we can measure the magnetic flux. The sensitivity is about 5 times 10 to the minus 18 Tesla Okay, that would be a very extremely small. Okay, so that's at the beginning. We will let you know how to measure the magnetic field. And the next section we are talking about the hard magnet. And the hard magnet is a very important material in the not only in the industry but also in the medical, because we always need a hard magnet to detect or just use that to scratch something. So I will show you later, and let me explain what is called the hard magnet. So the hard magnet for physics that we already talked about is the ferromagnetic material. Okay, so the ferromagnetic material with hard cohesivity are called magnetically hard material, and they were used to make a permanent magnet. So shown here are the list of some magnetic materials and their cohesivity. So okay, let me explain. The cohesivity is when we try to apply an external magnetic field, such like here is in the x-axis. If we want to apply the magnetic field to our materials, then these materials will increase its magnetization. That I already talked about last time. Magnetization is the sum of the magnetic dipole moment. So when we apply the field, increase the magnetic field, then the magnetization would be also increased with increasing magnetic field. And then they will go to a certain value that we would not increase magnetization anymore. And at this point we call it MS, which is the saturation magnetization. The subscript S means saturation. Okay. So when we reach the saturation magnetization, then we can try to decrease our applied magnetic field. So the magnetization will slightly decrease until to a certain value we call the remanence. We label here is called MR. R means remanence. So that means when we first excite all the magnetic moment, then when we first time remove the external magnetic field, then there will some reduced magnetization inside the material. So this is called the MR. And when we further decrease magnetic field, actually we increase to the negative directions, then the magnetization will keep decreasing until to a certain point, that with zero magnetizations. So this point would be intercept at a certain point and the exit in the exit B. So this point we call the HC, which is the cohesivity of this material. So you can imagine that the remanence means that the magnetization that we can store the magnetic energy here, and the cohesivity is the material that I can resist to demagnetize. So actually we were told a very important feature of the ferromagnetic material, that is in this area we call it, this is the magnetic energy product, which is the meaning of the magnetic energy that can store in the magnetic material. Okay, but here I want to first measure the cohesivity. HC is a kind of the index that how the stress of the magnetic material that can resist external magnetic field change. So shown here is the table of the cohesivity of some magnetic materials. So the list from top to bottom is the stress of the HC. So this is the first one we call supermarine, which is the very weak magnet. they only contains the cohesivity of 0.0025 OE. Okay, maybe you are not so familiar about the unit of OE, but that would be equal to the Gauss. And one is the stress of a magnetic field, and other is also that would be they are almost equal, but they have a little bit different definition. But you can think that one OE is equal to one Gauss. Okay, so 0.002 OE or 0.0025 Gauss means that would be very weak magnet. Compared to the magnetic field from the Earth, the magnitude of the Earth's magnet would be magnetic Earth would be 0.38 Gauss in Zhongli area. Okay, let's give you a very brief concept that the cohesivity of the supermassive is only 1/10 to the Earth's magnet. And when we go through this table, we will find for typical pure cobalt that would be 10 to the 900, and for the neodymium ion boron, that the number would be 10,000 to 12,000 Gauss. That would be very strong. The neodymium ion boron magnet, I will tell you, maybe you can find in the bookstore that that kind of magnet would be have the silver white color, and they would be have very strong magnetic force, different from those black color magnet. And nowadays the strongest magnet that we can make and you can purchase from the bookstore is a Samarian cobalt magnet. That would be contains the cohesivity is about 40,000 Gauss. That would be very very strong, and to discover this kind of hard magnet is very important for the industry, especially in the motor industry. So some important property used to compare permanent magnet are, there are 4 features. The first one is called resonance MR, okay, which is the measured stress of the magnetic field. So MR is located here. And the other is cohesivity. The materials resist to become demagnetized. So I just mentioned about this point, the intercept of the MB curve and at the B axis. And the third one we call energy product is B times H max. Okay, so actually that would be the area here. Okay, so the density of magnetic energy that's stored in the magnetic material. And the fourth feature that I do not show in this BH curve is the Curie temperature. So this is the temperature that when we increase the temperature, then the Curie temperature is the definition that the temperature at which the material loses its magnetism. Okay, so for more accurate, the loss is magnetism is not correct. Actually, that would be, we may say that this material just have a phase change from the ferromagnetism to paramagnetism. That would be more accurate. Any question here? No? Okay. So there is some definition. So we have a hard magnet. So you may think if there is any soft magnet. Yes, we did have this soft magnet, but the definition, how is the definition of hard magnet and soft magnet? So the definition of a hard magnet is if we have a cohesivity larger than 200 OE Øster, then we call this kind of compound is a hard magnet. And for the soft magnet, the cohesivity would be less than the 20 Øster. So the semi-hard magnet will in between the 20 to 200 Øster. So based on the JISC 2502/1989, the definition of the hard magnet have 4 catalog of based on its compositions. The first one we call the metal magnet. The second one is called a rare earth magnet. The third one is called ferrite. The fourth one is the composite magnet. So we have the 4 catalog of the hard magnet. So based on this we call the BH or MH curve. A good hard magnet exhibits some features. We need to have the high MR, which means a high remanence or reduced magnetization. And the other thing, we need to have the high cohesivity that we can resist the influence of the external or outer magnetic field. And we need to store a lot of magnetic energy inside this area, which is magnetic energy product is BH max. And we also want to have a very high TC, because if the TC is very close to room temperature, we will have a phase change from the ferromagnetism to paramagnetism. And in that situation, we cannot hold any magnetic energy product here, and we will not appear any magnetic field, and we cannot call this material become a magnet anymore. So we want to have a high TC in the hard magnet. Okay, so those are the definition of a hard magnet. But how to looking for the hard magnet? So let me record some feature about the spins that maybe you will have an idea how to embed this basic physical knowledge into looking for emerging material. So for the hard magnet, if we want to have a hard magnet, the first things we need to recall the equation called the average magnetic moment along the z-axis, the mu z bar. So the mu z bar is equal to g mu bj. Okay, we just ignore the Brownian function, because if we want to make hard magnet, we will align all these spin parallel to align to the one single directions. So the bj would be equal to 1, and the average magnetic along the z-axis will be equal to g mu bj. And here is g is the Landau g factor, and that will be depends on the value of the j, and the mu b is the constant, which is the ball magnum. So the important things, if we want to increase the magnetic moment, then we need to increase the j. And how to increase the j? We know the j is the total angular momentum. That is the sum of the orbital angular momentum and the spin angular momentum. So if you want to looking for the hard magnet, you need to find out the element that contains very large j. And of course, the j would be also follow the Hang's rule. So not all the element would be L plus j. For some element, they only contains the electrons that less than the half field share. So in that case, Hang's rule tells us the j would be equal to L minus s. So based on this rule, we can find out the maxima J from this choice. The first thing is we know the orbital, the subshell of the orbital is SPDF, which is corresponding to the angular momentum of 0, 1, 2, and 3. So if we want to let the J become maxima, you need to find out the element that contains F electrons. Okay, and the S is corresponding to the number of the electrons. One electron carries half spins, and if you can have a lot of electrons, then you can have many sum of the spins. So here we know the S orbital contains 2 electrons, and P is 6, D is 10, and F is 14. So based on this reason, we need to looking for the elements that contains F electron to give you the large J value. Of course, in this case, if the okay, let me there's one more thing that for the S orbital, let me change switch to this to here. Okay, and go to here. We know the S orbital can contains 2 electrons. If we have only 1 electron, then we have a spin value about half. But if we have 2 electrons here, then we will have the spin value of minus half. So the sum of spins would be half plus minus half, that would be equal 0. And for the P orbital, we have 3 sub orbital. This is Px, Py, and Pz. If we have 3 electrons, then the spin will parallel, and we also have the positive half value. So the S would be equal to 3 by 2. But if the P electron is fully occupied, P orbital is fully occupied, we have 6 electrons that would be arranged like this. We have parallel and anti-parallel spins. So here is positive half spins plus minus half spins, and also similar here, plus minus plus minus. So the total spin would be equal 0. So in this case, that tells you if we want to maximize J, we need to looking for the half field. The half field shell that will give you the maxima. Oh, sorry, S. That would be S. Oops. S. So in this case, maybe we need to find out the element that contains half field shell. For example, we need to find out the element that have F orbital but only have 7 electrons. So this is give you a direction that's how to looking for a strong magnet. So you just here is the periodic table. We know there's elements here are contains the S electron, and here are P electron, and here are the D electrons. So in this case, if we try to looking for the F electron, we can go here. This and here is the rare earth elements. The rare earth element contains the F electron, so that would be perfect to make the hard magnet. Of course, you may have a question: why not use this row? because you don't want to use the element here because most of this element contains radiations. So you don't want to use the magnet that contains the uranium, right? So the ideal element that can make a hard magnet is rare earth element. Okay, so the most important rare earth element is made I think the 90% rare earth element is made by China, so they can control the development of the hard magnet. So I remember there's almost 7 or 10 years ago, the China refused to export the rare earth element to Japan because Japan have a very strong industry in the making motor. So that would make the Japanese become very nervous because they cannot obtain the rare earth element, so they cannot make a very powerful motors for their vehicle or for the motor industry. That's because the ideal element that we can make strong hard magnet is need to have a large J, and the large J that we can apply in the industry or in our practical life is the rare earth element. So this is the reason that how to looking for the new material for hard magnet, and why we need to use the rare earth element to make a very strong magnet. And the other very important reason is, okay, I'm sorry about this. This is also a periodic table, but that would be right in Chinese. But actually, the location would be identical to the previous one. So in this periodic table, that represents the abundance of this element in the Earth. So we know in the Earth, the silicon is most rich element in the Earth, and so does the oxygen and the iron and sodium. You know, you can extract the sodium from the seawater, right? And the calcium and potassium and the hydrogen. But you can also find in the rare earth element they are also they are also rich. So rare earth is not really rare. It contains, I think the rare earth we call it rare is because they have very similar chemical properties. So if we want to separate the individual element from the earth is very difficult. So that's the reason we call this element is rare. Okay, so so for this reason, if we want to make a hard magnet, we can also use the rare earth element that compared to the iron that's very familiar for the hard magnet. The rare earth element is much better and it's not so hard to find in the earth. So if one country can control the rare earth, then they can control the motor industry. Okay, I know the time is up, so let's take a break for the 10 minutes. We will return in, after 10 minutes.